Well, we've looked at ionic compounds where we see the transfer of electrons from one atom to the other. We form cations and anions. Now we're going to look at covalent bond formation where we're actually sharing electrons. Unlike ionic compounds, we're actually looking at non-metal atoms, so typically two or more nonmetals that form these covalent bonds. And where we typically find these covalent compounds are in living things. This is where we see a lot of covalent molecules, particularly with carbon and hydrogen, because of carbon's unique ability to be able to make long chains of those carbon atoms. And we'll get into more into that in Chapter 4 when we start looking at organic compounds. For non-living material, those are typically ionic or metallic bonded materials, so we have different bonding patterns because of different types of elements involved in those systems. Now we've already talked about valence electrons because we looked at valence electrons to figure out what charge a species would take on when it forms an ion. For example, we look at chlorine, we see its electron arrangement is 2, 8, 7. It's going to take on one electron if it forms an ion because it wants to get to the 2, 8, 8 electron arrangement, so it would take on one electron. But chlorine doesn't always form an ionic compound. It can form an ionic compound, but it can also form a covalent molecule, and it's going to share electrons in such a way that it gets to get one more electron near it so that it will still have its 8 electrons around it. So just like looking at ionic bonding where we were worried about the valence electrons, we're still worried about the number of valence electrons here and looking at the electron arrangement and trying to get 8 electrons. But they're going to do it through sharing of electrons rather than the transfer of electrons. So let's look in a little more detail at chlorine, and what we see happening is that we have each chlorine atom which has 7 valence electrons. Those two chlorine atoms come close to each other, and as a result they're now sharing electrons. They've now formed this bond here in the middle, and so they have 2 electrons between them, and that's what forms the bond. Now when we see the bond forming, we usually change it and we write it a little bit differently, and we show it as a line connecting those 2 atoms, and that represents the bond. Now we say, well, we still have 14 electrons, how can both of them have 8? Remember, they're not worried about owning 8 electrons, they're just worried about being near 8 electrons. And so if I look at here the atom on the left, when I look at it, I see it has 6 electrons here that aren't involved in the bond, but I also see that it forms one bond, and it actually gets to count both of these electrons towards chlorine on the left, and the chlorine on the right also gets to count those electrons. So it doesn't make any more electrons. They don't magically appear when we put them together. They're just worried, do I have electrons close by? And they don't really care that they're having to share those electrons. All they're worried about is, are they there? And that shared pair of electrons make a covalent bond, and in this case makes a single bond. These electrons that are not involved in the bond, so these that are on the kind of outer parts of the atom, these are lone pairs of electrons, or non-bonding pairs of electrons. So we have bonding or shared pairs and non-bonding or lone pairs. So we'll also call these non-bonding because they aren't actually involved in the formation of the bond. So just like we looked at valence electrons to figure out how many electrons would be gained or lost by a particular atom when it formed an ion, what we see is that we're also going to have the number of valence electrons determine how many bonds we can actually form. So the number of bonds are based on the number of, quote, missing electrons. Well, what do we mean by missing? They weren't really there to begin with, so they're not really missing. What we're really talking about is how many are they missing in order to have 8 electrons around them, except for our good friend hydrogen, which remember only wants our 2 electrons. So we look at hydrogen, it has 1 electron, it would like 2, so it has 1 missing. And as a result, it's going to form 1 bond. When I look at carbon, there's 4 electrons. It needs 4 to get its 8, so it has 4 short, so 4 missing. Okay, that means 4 bonds that will form. And we'll talk about the different types of bonds that can form shortly. Nitrogen, we see there are 3 missing, so it's going to form 3 bonds. Oxygen has 2 missing. It will form 2 bonds, and fluorine, like chlorine, has 1 missing or is 1 away from being an octet, and so it will only form 1 bond. And what we have to do is, once we get the formula of a compound, we have to figure out how we arrange these atoms together so that everybody is happy, that everybody's going to get their 8 electrons around them, that will have For carbon, we'll have 4 bonds, nitrogen will have 3, each hydrogen will have 1, etc. And so that's our goal, is to figure out how to arrange them to get to that point. So we said carbon has to form 4 bonds, but that doesn't mean we have to form 4 single bonds. What we see is that we can form 4 bonds of any combination. So in this case, the first one here on the left, we formed 4 single bonds. That's still a total of 4 bonds. In the second example, we have 2 single bonds and 1 double. But because the double has basically 2 bonds, there's 2 pairs of electrons there. So 2 pairs of electrons being shared. Then what we're going to see is that we have 4 bonds around each of these. So we have, when we look at our one here on the left, we have 1, 2, 3, 4. On the right, we have 1, 2, 3, 4. This carbon atom still has 8 electrons around it. It has 4 electrons between it and its neighbor to the left, and 4 electrons between it and its neighbor to the right. So carbon still has 8 electrons total around it, as does the carbon here. Each single bond is 2 electrons, the double bond is 4 electrons, so again, carbon has 8 electrons around it. We can also see a triple bond, and when we have a triple bond, we actually have 3 pairs of electrons being shared. And we get a triple bond and a single bond. Now, why can't we have a triple bond and a double bond? Well, if I had a triple bond and a double bond, that will be a total of 5 bonds. I can't have 5 bonds. Carbon only forms 4 bonds. Never more, never less. Everything we look at for carbon will have 4 bonds. And this is going to be a critical thing when we get into looking at organic chemistry and helping us predict structures and understand how atoms are connected by remembering that fact that carbon forms 4 bonds. Now, the compounds we've looked at so far have primarily been our ionic compounds, or we've just been given a formula. We've not really worried about what they look like. Now, we're going to talk about how we represent them on paper here. In class, late in the next couple of days, we're going to look at how they are arranged in space. What is the geometry of those molecules? How are they arranged with respect to the other? What are the angles between those different bonds? So when I see an actual atom, what I actually see is something more like what is here on the left, that I'm seeing these atoms arranged. We see sharing of electrons here in between the carbon and hydrogen atoms. And we get that on the right here, or the middle section. We see we've drawn those as lines representing that pair of electrons in each of those bonds. And these are actually spaced evenly around that central atom. And again, we'll talk about the geometry in a little bit later. But when we write that on paper, the way we show that is what's here on the far right. We're just showing the connections between the carbon and the hydrogen. Now, this drawing doesn't show us anything about the geometry, or about the way these atoms are arranged. It only shows connections. From that information, we can then figure out what the geometry is, but this is not a ran out of room there. This is not a 3-dimensional drawing. It just shows how the atoms are connected to one another. We have to remember that while we draw things in 2-dimensional space on paper, we have to realize that we live in a 3-dimensional world, and these molecules will have a 3-dimensional geometry. So this table summarizes what we've already seen about our bonds. We said hydrogen is missing that 1 electron. It's going to form 1 bond. Carbon is going to form 4 bonds, and it can do that in a variety of ways. 4 single, 2 single and a double, 2 double, or 1 triple and a single. It doesn't matter as long as we end up with 4 bonds. Nitrogen can form 3 bonds, and much like carbon, it has options in how it does that. It can form 3 single bonds, a double and a single, or a triple bond, but its maximum is 3 bonds. For oxygen, we can see 2 bonds, so we see 2 single bonds or 1 double bond. In fluorine, it only has 1 bond. The halogens usually only form 1 bond, and for our purposes, that's really pretty much all we're going to see. There are some more exceptions with those halogens as we get into some more advanced compounds. Sulfur, we see, has 2 bonds. And unlike oxygen, it typically will not form a double-bonded sulfur. So when you have a sulfur, you know what it's going to look like. Just like with hydrogen, you know it's only going to form 1 bond. And it's looking at these different arrangements that what we can do is arrange these different molecules, these pieces, assemble them together and build molecules. So it's kind of like putting Legos together. If I have a bunch of pieces of Legos, I got to figure out how to put them together to make a house or make a building, something that looks like my house. I can't just throw them all together and expect everything to be perfect. I want to make sure that I connect them in such a way that they are happy elements, that they have their octet, that they have 8 electrons around them. So as we're looking at the examples where we're drawing structures, what we're going to do is actually use this table to assemble the molecules. Now keep in mind that if you're doing this on the homework, you've got this table available. If I'm expecting you to actually draw a molecule on the exam, you're going to have this table available. I'm not expecting you to memorize this. I just need you to know how to use it. Now, if you're given a structure and don't have to draw it yourself, you should be able to recognize if it's a good structure or not, if it's a reasonable structure, based on simply counting the number of electrons around each atom, because every atom wants 8 electrons. So let's look at some examples of how we actually assemble these molecules using the information in the table. So I've looked at the elements that are involved in my molecule. I have hydrogen, which I know will only form one bond no matter what, and oxygen, which when I look at that, I'll see that I can either form 2 bonds, so I have 2 single bonds and 2 lone pairs, or I'll form a double bond and have 2 lone pairs. And what I want to do is actually figure out how can I assemble these atoms such that everybody is happy, everybody gets the right number of bonds, everybody gets their octet. And so the first thing I'm going to try is actually putting my oxygen with my 2 lone pairs and my double bond, and I'm going to attach a hydrogen to it. Now before I even put another hydrogen in there, what I see is that this hydrogen is not happy. It has 4 electrons around it because it has 2 bonding pairs. It's forming 2 bonds, and we just said hydrogen will only form single bonds. So we can see that this is not going to be a possibility. I could play around with this and see if there was any, could put a hydrogen and then connect to the oxygen. But what I'm seeing here already is now I've got my hydrogen with 2 bonds. We know that's not going to happen either, and so neither of those are possibilities. So what I'm going to do is actually, let's try the oxygen with 2 single bonds. It has 2 lone pairs of electrons here on the oxygen atom. So I've got my oxygen each with 2 single bonds, and I make my hydrogens on either end of those bonds. Now what I have is a hydrogen atom with 2 electrons around it because there's 2 electrons in that bonding pair, and hydrogen gets to count those for itself, as does the other hydrogen. But what I also see is that my oxygen, and we're going to draw a circle so we can see all what's included in there, is that oxygen can count the electrons in those bonds as well. And so now oxygen has 8 electrons around it. It has 8 electrons because it has 4 bonding electrons, or 2 pair. Okay. So 2 pair of electrons plus 4 non-bonding, which is also 2 pair of electrons. So we get a total of 8 electrons. So now oxygen is happy because 1, it has 8 electrons, and 2, it has 2 bonds, which we know that's what oxygen wants. Hydrogen has 1 bond. Each hydrogen has 2 electrons. Everybody is happy. And this is the kind of thing you'll need to do with different molecules. You're going to have to try trial and error to figure out how those atoms are connected to one another. Now let's look at our example of CO2. Apologies for the lovely artwork here. Some of my images did not come through when I switched over to the iPad. So what we have here is our CO2, and we're going to have to, again, see how we can put these atoms together so that when we do, everybody has an octet and every atom has the right number of bonds. And so the first thing I will try when I'm looking at CO2 is I'm going to say, well, let's say that we have carbon in the middle, and let's look at making 4 single bonds. Well, this isn't going to work because I only have 2 oxygen atoms. I've run out of oxygen atoms. I've got nothing to put in these 2 spots, and if there's nothing to go there, then I can't form that compound. So that's not going to be a reasonable structure. I say, well, if I've got carbon and I have 2 oxygens, I really only have 2 choices, because when I look over here at the right side where my options are, if I've got a carbon, I can say, well, my carbon is either going to make 2 bonds here with 2 double bonds, or with a single and a triple bond. And so we'll actually draw out both of those structures so we can compare them. So I say let's start with our carbon with 2 double bonds. And each of our oxygens has a lone pair, two lone pair rather. And let's look at a carbon with a triple bond and a single bond. And we're kind of running into a problem here because remember, oxygen wants another bond, but there's nobody to bond to. We're out of atoms. And so when we look at this, we say, well, you know, carbon's happy. It's got its 8 electrons around it. Got a couple too many electrons there in my oxygen. But carbon's happy because it has 8 electrons. However, this oxygen has 10 electrons, so it is not happy. And over here, poor oxygen only has 1 bond, and therefore it's got these other bond it wants to form that it can't. So there's something wrong with this structure, and it's going to make it not an option, which leaves us with the 2 double bonds. So we go back and look at all of our atoms, and we say, well, oxygen has 2 bonds, great. This oxygen also has 2 bonds, and carbon has 4 bonds. So we've checked the number of bonds. We found that to be good. Then we can check the number of electrons around each atom. So I look at the oxygen. I see my 8 electrons, 2 non-bonding pairs, 2 bonding pairs for a total of 8 electrons. Then I can look at my carbon, and I see I've got 4 bonding pairs of electrons. That gives me 8 electrons around the carbon, so carbon is happy. And then I look at the electrons around the oxygen. I have 2 pair bonding and 2 pair non-bonding for a total of 8 electrons. Remember, I can count electrons twice for the purposes of the structure because they're sharing those electrons. They both get to count them. And so what I see is that this is going to be my preferred structure because all my atoms are happy with the right number of bonds and with the right number of electrons. Let's look at one more example here with NH3. Remember, I've got to have each atom with 8 electrons around it, but also to follow my bonding rules. Hydrogen can form 1. Nitrogen's only going to form 3 electrons. So I can look at this, and based on what I've learned in the previous 2 example problems, I see that hydrogen is only going to form 1 bond. And as a result, hydrogen has to be what we call a terminal atom. And what that means is that it's always on the end or the edge of a molecule. I'm never ever going to see hydrogen, okay, and have it in between other atoms here. I'm not going to see hydrogen form 2 bonds. And so as a result, I know hydrogens always have to kind of be on the outside of the molecule. And if that's the case and I have 3 of those hydrogens, then what I see has to happen is that the nitrogen has to be in the middle and the hydrogens have to be around it. I know hydrogen can only form a single bond, and I know nitrogen needs 3 bonds, and so I can put 3 bonds. So now that meets my bonding requirements of the hydrogen and nitrogen. When I look back at my model over here, when I use 3 single bonds with nitrogen, I notice that I also have a lone pair of electrons on that nitrogen atom. Again, you don't have to worry about predicting when we're going to have lone pairs of electrons. You just have to know how to use the templates and these kind of building blocks that are given to build these molecules. And so what we have is hydrogen attached to nitrogen. So if I look at each hydrogen atom, I see that it has 2 electrons, has 2 electrons around it, which makes it happy, doesn't want 8. If I look at my nitrogen, I see it has 3 bonding groups, so 3 pairs of electrons for bonding, so that's a total of 6 bonding electrons, and 2 non-bonding electrons in that lone pair for a total of 8 electrons on nitrogen. So it is very happy. So again, the best way to learn this is by practice. Obviously, you're not going to be using mastering on the exam. There may be some exams where we actually draw structures out. I will let you know about those in advance. Look on mastering either under the additional tutorials or within the assignment. There should be at least one question that is set for practice so that you can practice drawing these structures where there's no points, and so you can kind of play with the drawing system. Do make sure your Java is updated before you go into the assignment. If you have any questions, let me know. We can talk about this. Office hours, go to the study, go to the Learning Center, post on Piazza, whatever you need to do, but make sure you get help and get those questions answered. Have a great day.